Hello, everyone. Welcome to today's presentation. I'm excited to be here with you. We will be exploring gas diffusion and respiratory gas exchange. The title of our talk is Gas Diffusion and Respiratory Gas Exchange, and our focus will be understanding how oxygen and carbon dioxide are transported in the human body. Over the next few slides, we'll cover the mechanisms behind this vital process, helping us appreciate how our respiratory system keeps us alive and well. Let's get started. Let's start by exploring the fundamentals of gas diffusion and how it relates to our respiratory system. Gas diffusion is the process by which gases move from areas of higher partial pressure to areas of lower partial pressure, driven by differences in concentration. This movement is essential for oxygen to enter our blood and carbon dioxide to leave it. Now, a key concept here is the partial pressure gradient. The greater this gradient, the faster the gases diffuse. That's why the difference in partial pressures between alveolar air and blood is so crucial for efficient gas exchange. Gas diffusion happens simultaneously for oxygen and carbon dioxide, often occurring at the same time across the alveolar capillary membrane. This simultaneous process ensures that our tissues receive oxygen and that carbon dioxide is efficiently removed. Additionally, the diffusion process isn't limited to the alveoli. It also occurs through the circulatory system, where gases are transported via blood to reach and leave tissues. This highlights the importance of both diffusion and circulation working together seamlessly. Understanding the respiratory exchange ratio, or R, is also vital. It tells us the ratio of carbon dioxide produced to oxygen consumed, giving insight into metabolic processes and energy expenditure. The partial pressure diffusion gradients are influenced by differences in atmospheric, airway, and alveolar partial pressures of oxygen, specifically PO2. These gradients are critical for maintaining effective oxygen uptake and carbon dioxide removal. We also use the alveolar air equation to estimate alveolar PO2, accounting for factors like inspired air, carbon dioxide levels, and others. This helps us understand how alveolar oxygen levels change under different conditions. All these concepts tie together to give us a comprehensive picture of how gases move in and out of our body, ensuring our tissues get the oxygen they need and waste gases are expelled efficiently. Let's delve into the fascinating process of gas diffusion and how it plays a crucial role in our respiratory system. On this slide, we'll focus on the concept of diffusion itself and the key sites where it occurs in our lungs and tissues. First, diffusion is basically the net movement of molecules from an area of higher concentration to an area of lower concentration. Think of it as molecules naturally spreading out to balance things out. This process is fundamental to how gases like oxygen and carbon dioxide are exchanged in our bodies. In the respiratory system, diffusion primarily happens at two important sites. The first is the alveolar capillary membrane. Here, oxygen from the inhaled air passes through the thin alveolar walls and enters the blood, while carbon dioxide moves from the blood into the alveoli to be exhaled. This exchange is vital for oxygenating our blood and removing waste gases. The second site is at the tissue level. Once oxygen is in the blood, it travels to tissues, where it diffuses into cells. Simultaneously, carbon dioxide, a waste product from cellular metabolism, diffuses out of the cells into the blood to be carried back to the lungs. This whole process of diffusion, from lungs to tissues, is essential for maintaining proper gas exchange. It supports cellular metabolism, ensuring our body's cells receive the oxygen they need and can get rid of carbon dioxide efficiently. So, understanding these key sites and the diffusion process helps us appreciate how critical our respiratory system is for sustaining life. Let's talk about gas diffusion and how respiratory gases are exchanged in the body. The key idea here is that gases move due to differences in their partial pressures, which creates what's called a diffusion gradient. This means that gases naturally tend to move from areas where their partial pressure is higher to areas where it's lower. For instance, oxygen moves from the alveoli, where its partial pressure is high, into the blood, where it's lower. Conversely, carbon dioxide moves from the blood, where its partial pressure is higher, into the alveoli to be exhaled. This process continues until equilibrium is reached, meaning the partial pressures of gases are equal on both sides of the membrane. This gradient-driven movement is crucial because it ensures that oxygen is efficiently taken up by the blood and carbon dioxide is effectively eliminated. Understanding this mechanism helps us appreciate how our respiratory system maintains the balance necessary for proper gas exchange, supporting overall respiration and cellular function. Let's take a closer look at gas diffusion and respiratory gas exchange. This process is essential for maintaining balanced gas levels in both the blood and alveoli. It's a dynamic exchange, meaning it's constantly happening to keep everything in equilibrium. Now, what's particularly interesting is that two gases can diffuse at the same time, but in opposite directions. This occurs because their partial pressure gradients are oriented in opposite ways. For example, carbon dioxide diffuses from the blood into the alveoli, where its partial pressure is lower. This allows CO2 to leave the blood efficiently. At the same time, oxygen diffuses from the alveoli into the blood, again moving down its partial pressure gradient. This simultaneous movement of gases, oxygen in, carbon dioxide out, is what we call independent gas movement. And an important point to remember is that each gas moves independently down its own partial pressure gradient during diffusion. So, even though both gases are diffusing simultaneously, they don't interfere with each other. They follow their own pressure gradients. This entire process is crucial for effective respiration and ensuring that oxygen gets into our blood and carbon dioxide is expelled properly. Now, let's look at how gas diffusion and respiratory gas exchange work together in this vital process. Reoxygenation in the lungs is a continuous cycle. Once the blood has delivered oxygen to the tissues, it needs to be reoxygenated, so it gets pumped back to the lungs for that process to happen again. This is what we mean by the cycle repeating. Deoxygenated blood, which is blood that has released its oxygen, returns to the heart through veins. From there, it gets pumped to the lungs. At the lungs alveoli, oxygen diffuses from the tiny air sacs into the pulmonary capillary blood. Simultaneously, carbon dioxide, a waste product from the tissues, diffuses out of the blood into the alveoli to be exhaled. Once the blood is reoxygenated, it travels through the arteries to reach various tissues throughout the body. At the tissues, oxygen moves from the blood into the cells, a process called diffusion, providing the cells with the oxygen they need for energy. Meanwhile, carbon dioxide produced by the cells diffuses back into the blood, ready to be carried away. This entire system is beautifully efficient, ensuring that oxygen is constantly supplied to tissues and waste gases are removed. It highlights how diffusion through the circulatory system plays a crucial role in maintaining our overall respiration and cellular function. Now, let's focus on how oxygen diffuses in the lungs. When we breathe in, oxygen enters the alveoli, those tiny air sacs in our lungs. From there, oxygen moves across the thin walls of the alveoli into the surrounding pulmonary capillaries. This process is driven by a concentration gradient, meaning oxygen moves from an area of higher concentration in the alveoli to a lower concentration in the blood. This diffusion is crucial because it allows oxygen to enter our bloodstream, where it binds to hemoglobin and is then transported to tissues throughout the body. Understanding this diffusion process helps us appreciate how efficiently our lungs are able to oxygenate our blood, supporting the overall theme of respiratory gas exchange. Now, let's look at how oxygen gets from the lungs to the tissues that need it most. Once the blood has been oxygenated in the lungs, it travels through the arteries. Think of these as highways carrying oxygen-rich blood. This blood is then directed toward the peripheral tissues, which includes all the organs and cells throughout your body. The key idea here is that oxygen doesn't just stay in the blood. It needs to be delivered efficiently to support cellular functions. As the oxygen-rich blood reaches these tissues, oxygen diffuses out of the blood and into the cells, fueling processes like energy production. This entire process is a vital part of the larger respiratory system, ensuring that oxygen is effectively transported from where it's taken in, your lungs, to where it's used, your tissues. Understanding this journey highlights how crucial the coordination between the respiratory and circulatory systems really is. It's this seamless delivery that keeps every part of your body functioning optimally. Now, let's talk about what happens at the tissues during gas exchange. When blood reaches the tissues, oxygen needs to move from the blood into the cells, and at the same time, carbon dioxide produced by the cells needs to leave the tissues and enter the blood. This process is driven by differences in partial pressure. Oxygen moves from an area of higher concentration in the blood to lower in the cells, while carbon dioxide moves in the opposite direction. Essentially, oxygen diffuses into the cells to support their metabolic activities, and carbon dioxide, a waste product, diffuses out of the cells into the blood so it can be carried back to the lungs for removal. This exchange is crucial because it ensures that our tissues receive the oxygen they need and that waste gases are efficiently removed, completing the respiratory cycle. It highlights the importance of diffusion as the underlying mechanism for gas exchange at the cellular level, which ties back to the overall theme of how our respiratory and circulatory systems work together seamlessly. Now, let's talk about what happens after the gases are exchanged in the lungs. Deoxygenated blood, which is blood that has given up its oxygen and picked up carbon dioxide, needs to return to the heart to be sent to the lungs again for reoxygenation. This return journey happens through the veins. Veins are specialized blood vessels that carry this deoxygenated blood back toward the heart. It's a crucial part of the circulation process because it ensures that the blood is continuously cycled through the lungs for gas exchange. This step ties into the overall theme of how our respiratory and circulatory systems work together seamlessly to keep our bodies supplied with oxygen and to remove waste gases like carbon dioxide. So, understanding this return flow is key to appreciating the entire process of respiration and gas exchange. Let's talk about reoxygenation in the lungs. After the blood has delivered oxygen to the tissues, it needs to be reloaded with oxygen so it can continue to support the body's needs. This process begins as the blood is pumped back to the lungs through the pulmonary arteries. Once in the lungs, the cycle repeats. Gases diffuse across the respiratory surfaces, allowing oxygen to enter the blood and carbon dioxide to leave. This continuous process ensures that the blood stays rich in oxygen, maintaining proper tissue function. It's a vital part of the overall respiratory cycle, highlighting how the lungs and circulatory system work together seamlessly to keep us alive and well. Now, let's discuss the typical R value, which is about 0.8. This means that, for every unit of oxygen leaving the alveoli, about 80% of that amount of carbon dioxide enters the alveoli. This ratio gives us a useful way to understand the balance between oxygen consumption and carbon dioxide production in the body. Essentially, it reflects our metabolic activity, how much oxygen our tissues are using, and how much CO2 they produce as a byproduct. At rest, approximately 200 milliliters of carbon dioxide diffuse from the blood into the alveoli each minute. This process is crucial because it helps us get rid of CO2, maintaining proper acid-base balance. Simultaneously, pulmonary capillary blood removes about 250 milliliters of oxygen from the alveoli each minute during rest. This oxygen is then transported to meet the body's energy demands. Finally, to clarify, the respiratory exchange ratio, or R, is defined as the ratio of carbon dioxide diffusion into the alveoli to the oxygen diffusion out. It essentially tells us how much CO2 is being produced relative to oxygen consumption, which is a key indicator of metabolic activity and helps us understand respiratory efficiency. Let's take a closer look at gas diffusion and how respiratory gas exchange works in the lungs. The key point here is that the oxygen diffusion gradient between the alveoli and venous blood is much larger than that for carbon dioxide. This large gradient is essential because it drives efficient oxygen transfer into the blood. For oxygen, the partial pressure in the alveoli is about 100 mmHg, while in venous blood, it's roughly 40 mmHg. This big difference creates a strong diffusion gradient, making oxygen move rapidly into the blood where it's needed. Now, when we look at carbon dioxide, the situation is a bit different. The partial pressure of CO2 in venous blood is around 46 mmHg, and in the alveoli, it's about 40 mmHg. Although this gradient is smaller than that for oxygen, it's still sufficient to allow effective CO2 to leave the blood and enter the alveoli for exhalation. Another important point is that venous blood has a slightly higher PCO2 compared to alveolar PCO2, which facilitates this exchange. The lower partial pressure of CO2 in the alveoli compared to venous blood means CO2 can diffuse out efficiently. In summary, the differences in partial pressures, especially the large oxygen gradient, are crucial for efficient gas exchange. The higher the gradient, the more effective the diffusion. This balance ensures our blood becomes oxygen-rich and CO2 depleted as it passes through the lungs, supporting overall respiration and cellular function. Let's talk about the partial pressure of oxygen in the atmosphere. It's approximately 160 mmHg, which we get by multiplying the atmospheric pressure of 760 mmHg by 0.21, the percentage of oxygen in air. This value is important because it sets the baseline for oxygen availability. Now, when we consider the air in our airways, things change a bit. Humidification occurs as the air travels through the respiratory tract, which adds moisture and causes the partial pressure to decrease slightly. So, the airway PO2 drops to about 150 mmHg, calculated as 760 minus 47 times 0.21. The reduction is mainly due to the water vapor added during humidification. Moving further into the lungs, in the alveoli, the PO2 decreases even more. This is because carbon dioxide diffuses out of the blood into the alveoli, reducing the oxygen pressure further, to roughly 100 mmHg. These changes in partial pressure are crucial because they drive the diffusion of gases, ensuring oxygen moves into the blood and carbon dioxide moves out efficiently. This process is fundamental to respiratory gas exchange and highlights how the body maintains proper oxygen levels for cellular function. Now, let's explore the purpose of the alveolar air equation. Its main goal is to calculate the partial pressure of oxygen within the alveoli, known as PaO2. This value is crucial because it helps us understand how much oxygen is available for gas exchange in the lungs. The formula itself might look complex at first glance, but it's designed to accurately estimate alveolar oxygen levels by considering key factors. The equation is PaO2 equals the barometric pressure minus water vapor pressure, multiplied by the fraction of inspired oxygen, and then subtracting the arterial carbon dioxide pressure times 1.25. Let's break down the key variables. PB is simply the barometric pressure, which changes with altitude. pH2O is the water vapor pressure, which is typically 47 mmHg at body temperature. FiO2 is the fraction of inspired oxygen, so whether you're breathing room air, which is about 21%, or oxygen-enriched mixtures. And PaCO2 is the arterial carbon dioxide pressure, reflecting how much CO2 is present in the blood. Why is this formula so important? Because it accounts for humidification and the presence of CO2, giving us a more accurate estimate of alveolar oxygen tension under different conditions. This is especially useful in clinical settings, whether we're assessing a patient breathing room air or receiving 100% oxygen. In summary, the alveolar air equation helps us understand the oxygen available in the lungs, which is fundamental for evaluating respiratory function and tailoring treatments. It's a vital tool in respiratory physiology, linking the concepts we've discussed about gas diffusion and oxygen exchange directly to clinical practice.